December 16, 1944. 0531 hours. Monschau, German-Belgian border. Colonel Oscar Alfred Axelson of the U.S. 46th Artillery Group stared at the restricted ammunition crates in the pre-dawn darkness, knowing his next decision would breach standing orders from the highest levels of Allied command. Through his field glasses, he could see German forces massing for what would become Hitler's final desperate offensive in the West, Operation Watch on the Rhine. The 38th Cavalry Squadron defending the northern shoulder of what history would call the Battle of the Bulge was about to be overwhelmed. "Sir, German artillery preparation has begun," his operations officer reported. "The 38th is requesting immediate fire support." Axelson turned to the stacks of shells marked with the classified designation T-98, proximity-fused rounds that had been strictly forbidden for use over land since their development. The technology was so secret that even most American commanders were unaware of its existence. These shells held miniaturized radio transmitters that would detonate roughly 30 feet above the ground, producing a lethal cone of fragments that made traditional foxholes worthless as protection. "Load the VT shells," Axelson ordered, using the code name Variable Time to confuse enemy intelligence. "We're going to need everything we have." Within 47 minutes, Axelson's unauthorized action would introduce German ground forces to a weapon that would reshape the final months of World War II. The shells that erupted above German positions contained technology so advanced that German scientists had once deemed it impossible. Each fuse embodied an industrial accomplishment revealing the true gulf between American manufacturing strength and German assumptions about their enemy. The mathematics of death was about to be rewritten. Every shell would detonate at approximately 30-foot altitude, creating a cone of supersonic steel fragments traveling at 3,000 feet per second, carpeting a 60 yd radius with deadly effect. No amount of digging, no depth of foxhole, no thickness of overhead cover constructed under battlefield conditions could matter against this rain of metal from above. The proximity fuse represented the third most significant technological innovation of World War II, behind only radar and the atomic bomb, a ranking affirmed by official U.S. military analyses. Yet unlike those technologies, its very existence remained unknown to German forces until they were dying beneath its effects. The device was elegantly simple in concept, nearly impossible in execution: a miniature radio transmitter and receiver small enough to fit in the nose of an artillery shell, durable enough to survive 20,000 gs, and sophisticated enough to sense its distance from the ground and detonate at the ideal height for maximum lethality. Each fuse held 4 vacuum tubes, not 5, as occasionally claimed, forming a complete radio station compressed into a space smaller than a coffee cup, hardened to endure forces that would liquefy human tissue. Development began in 1940, consuming $1 billion in 1940s dollars, roughly $15 billion today. By late 1943, American factories were producing 40,000 proximity fuses daily, a rate that would rise to 70,000 per day by the war's end. The British scientific mission that first observed the technology described it as the most remarkable scientific feat of the conflict. Production statistics revealed American industrial superiority, exactly 22-73 for 81 proximity fuses built between 1942 and 1945, with 21,685,157 shipped for combat and 388,324 allocated for testing. Each fuse contained about 130 components machined to tolerances of 0.100th of an inch and assembled in clean rooms by 110,000 workers, many unaware of what they were creating. The power problem was solved by an ingenious wind-driven generator activated only after the shell left the barrel. A small propeller, shielded during acceleration, extended into the slipstream and generated electricity to charge the capacitors powering the radio circuit at 180 to 220 MHz. This meant the fuse remained inert until fired, safe to handle, impossible to detect, and resistant to jamming until the final seconds of flight. The first large-scale employment of proximity-fused shells against ground forces began at 0618 hours on December 16, 1944, exactly 47 minutes after the German assault commenced. Colonel Axelson's 46th Artillery Group fired without official sanction, responding to an immediate tactical emergency. General Eisenhower would not formally request clearance until December 19, with all restrictions lifted by December 21. The effect was immediate and devastating. German infantry advancing in the pre-dawn gloom dove for their prepared foxholes as American artillery opened fire, standard procedure they had practiced countless times. But instead of striking the earth, the shells burst overhead. Fragments rained downward at angles that rendered foxholes ineffective. The 99th Infantry Division's after-action report documented the results. VT-fused concentrations on German assembly areas near Krinkeln caused extraordinary casualties among leading battalions within 12 minutes of the fire mission's start. Enemy medical services were overwhelmed. Advancing troops were forced to step over their own dead to continue the attack. By December 23, military intelligence estimated that proximity-fused rounds had killed roughly 2,000 German soldiers during the fighting around Malmedy, where artillery battalions fired with great effect against SS units. Some attackers became so unnerved they charged directly into artillery fire, shouting "Kamerad!" The psychological shock exceeded even the physical destruction. To understand why proximity fuses rendered traditional defensive positions obsolete, one must grasp the physics of airburst lethality. A standard shell detonating on impact sends 50% of its fragments into the earth, 45% outward, and only 5% upward. A soldier in a well-constructed foxhole had a 90% chance of surviving conventional artillery. The proximity fuse overturned those calculations completely. Detonating at 30-foot altitude, nearly all fragments traveled downward or outward in an inverted cone. The lethal radius expanded from 25 yards for a ground burst to 60 yards for an airburst. More crucially, fragments struck at 30 to 45 degrees angles, perfect for entering foxholes, trenches, and rifle pits. The lethal fragment area increased from 60 square feet with contact fuses to 3,000 square feet, a 50-fold improvement that rendered traditional fieldworks largely ineffective. This was not a mere improvement in artillery effectiveness. It was a fundamental transformation in how artillery could be used against infantry. The shells themselves became monuments to American precision manufacturing. The miniaturized components had to function after experiencing forces that would destroy conventional electronics. The 4 vacuum tubes, a triode for oscillator/detector functions, a pentode for amplification, a theron as the trigger switch, and occasionally a diode for rectification were specially hardened versions that bore no resemblance to their commercial counterparts. The proximity fuse's development represented American scientific industrial cooperation at its peak. In August 1940, the British TISAD mission had shared their military secrets with America, including early radar work and the theoretical concept of a proximity fuse. British scientists had proven the theory, but lacked industrial capacity to develop and mass-produce the device. The National Defense Research Committee, formed in June 1940, made the proximity fuse their second priority after radar. Johns Hopkins Applied Physics Laboratory became the development center while American industry tooled up for production. The challenges were staggering. The fuse had to withstand 20,000 gs of acceleration, function in temperatures from -50 to +120 degrees Fahrenheit, spin at up to 30,000 revolutions per minute, and operate reliably after months of storage in conditions ranging from humid Pacific islands to frozen European depots. Section T, the code name for the proximity fuse project, employed 3,000 scientists and engineers at its peak. They developed new plastics that wouldn't shatter under acceleration, miniature vacuum tubes that could withstand forces that would destroy normal electronics, and assembly techniques achieving accuracy measured in 10,000 of an inch. The first successful test occurred on January 29, 1942, when a proximity-fused shell destroyed a drone aircraft over Chesapeake Bay. By August 1942, the USS Cleveland was equipped with proximity-fused anti-aircraft shells. The results were spectacular. Japanese aircraft kills increased dramatically. The USS Helena made history on January 5, 1943, shooting down a Japanese dive bomber off Guadalcanal using only 4 proximity-fused shells. But the technology was deemed too secret to use over land where the enemy might recover unexploded shells. This restriction held until the German offensive in the Ardennes threatened to split Allied forces, forcing field commanders like Colonel Axelson to make unauthorized decisions that would prove correct. Before their ground deployment, proximity fuses had already proven revolutionary in naval warfare. Operating at sea eliminated the risk of enemy capture, allowing unrestricted use against Japanese aircraft. The statistics were compelling. Ships using proximity fuses required an average of 310 rounds per aircraft kill compared to 1,162 rounds for conventional ammunition. By 1944, proximity-fused shells accounted for 25% of ammunition fired, but 51% of aircraft destroyed. During the Battle of the Philippine Sea in June 1944, proximity fuses helped create what became known as the Great Marianas Turkey Shoot. With Japanese aircraft losses exceeding 400 planes, the technology that would devastate German infantry had been perfected against Japanese pilots. The British had begun using proximity fuses against V-1 flying bombs. On June 12, 1944, just days after D-Day, anti-aircraft batteries along the English coast increased their kill rate from 17% to 79% within 4 weeks. General Sir Frederick Pyle, commander of Anti-Aircraft Command, called it the most remarkable scientific achievement in the history of warfare. These successes made the restriction on ground use increasingly difficult to maintain. Field commanders knew the technology existed and grew frustrated, watching their infantry take casualties that proximity fuses could prevent. The Battle of the Bulge crisis finally broke this bureaucratic logjam. German intelligence had actually received warnings about proximity fuses. In October 1944, General Feldmarschall Albert Kessel-Ringstaff noticed dramatic increases in Luftwaffe losses to Allied anti-aircraft fire. They recovered metal fragments with unusual scoring patterns suggesting airburst detonation. Kessel-Ring's report to OKW Oberkommando stated, evidence suggests Americans possess altitude-triggered ammunition. If adapted to ground artillery, effects on infantry would be catastrophic. Recommend immediate investigation of countermeasures. The response from Berlin found in captured archives dismissed his concerns. Technical evaluation concludes proximity detonation under battlefield conditions impossible. American anti-aircraft improvements attributed to radar direction and increased gun density. No action required. This dismissal would cost the Wehrmacht dearly. German scientists had actually attempted to develop proximity fuses since the early 1930s, creating 30 to 50 different designs, including acoustic fuses triggered by engine sound, electrostatic field devices, and radio-based systems. None reached operational status. Hitler's 1940 directive terminating all development that couldn't reach production within 6 months effectively killed their program. The irony was profound. During the Battle of the Bulge, German forces captured approximately 20,000 proximity fuses, but never recognized what they had. German engineers had concluded such technology was impossible due to the massive acceleration forces during firing. They literally held the intelligence coup of the war in their hands without realizing it. 5 American companies conducted final assembly of proximity fuses. Crosley Corporation 5.2 million units. Sylvania 5.7 million. RCA at 2 plants 5.9 million combined. Eastman Kodak 2.4 million and McQuay Norris 2.9 million. Sylvania's Ipswich, Massachusetts plant was the single highest producing location, accounting for 26% of total output. The Crosley Corporation's Cincinnati plant employed 8,000 workers, producing up to 16,500 proximity fuses daily at peak production. Their quality control detected defects measuring 15,000th of an inch. The plant consumed more electricity daily than entire German cities. Air conditioning maintained temperature within 2 degrees to prevent thermal expansion affecting tolerances. Quality control rejected 28% of completed units that failed to meet specifications. This rejection rate, which would have been catastrophic in German production, was acceptable to American planners because production volume was so massive. They could afford to destroy more precision components daily than Germany produced monthly. Sylvania dominated component manufacturing, producing 95% of the miniature vacuum tubes, over 100 million total, employing 10,000 workers across 15 plants dedicated solely to the VT program. Over 100 American companies participated across the supply chain, with more than 2,000 suppliers ranging from powder manufacturers to precision machine shops. The workforce was predominantly female. At Sylvania's Ipswich plant, 9,000 of 10,000 workers were women, many recruited from local communities. They worked in clean rooms with filtered air, using microscopes to verify component placement within tolerances of 20,000 of an inch. Each worker typically performed one specific task, repeated thousands of times per shift. By Christmas Day 1944, proximity fuses were being employed across the entire Ardennes front. The U.S. Army fired 200,000 proximity-fused shells during the Battle of the Bulge. General Patton, initially skeptical of the new technology, became a convert after witnessing its effectiveness. On December 25 to 26, Patton's Third Army reported killing approximately 700 Germans by actual count at Ecton using proximity-fused artillery. His famous assessment, "The funny fuse won the Battle of the Bulge for us." This from a commander who had previously favored tanks and mobile warfare over artillery. The psychological impact on German forces was documented through prisoner interrogations. Captured soldiers repeatedly described feeling helpless against artillery that exploded overhead. Traditional defensive training emphasized taking cover in depressions, foxholes, or trenches. Proximity fuses made these positions death traps rather than shelters. 1. Captured German officer told interrogators, "Your shells explode exactly at treetop height. Always the same height. We tried everything, deeper holes, concrete covers, dispersal. Nothing worked." The consistency of the 30-foot detonation height achieved through precise radio measurement created a predictability that was paradoxically more terrifying than random impacts. The Hürtgen Forest Battle, which had raged since September 1944, transformed when proximity fuses were authorized for use on December 18. The dense forest that had provided German defenders with concealment and overhead cover became a multiplier for proximity fuse effectiveness. Tree bursts had always been deadly, but they were difficult to achieve deliberately with time-fused shells. Proximity fuses detonated consistently at optimal height, whether over open ground or forest canopy. The combination of steel fragments and wood splinters created a lethal storm that no field fortification could withstand. The 4th Infantry Division's artillery fired 12,000 proximity-fused rounds in the first 48 hours after authorization. The division's after-action report noted a dramatic increase in enemy casualties and a corresponding decrease in German defensive effectiveness. Medical stations reported wound patterns they hadn't seen before. Deep puncture wounds from above, concentrated on shoulders and heads. This battle became a grim laboratory for understanding proximity fuse effects. Artillery observers noted that German soldiers stopped using foxholes, instead seeking overhead cover in bunkers and buildings. This forced them into concentrated positions that became targets for conventional high-explosive shells, creating a tactical dilemma with no good solution. Operation Grenade, the Allied offensive to reach the Rhine, began February 23, 1945. The 9th Army fired hundreds of thousands of proximity-fused shells in the first week. German defensive positions carefully prepared over months proved vulnerable to airburst attack. The Wehrmacht issued increasingly desperate directives attempting to counter proximity fuses. A February 10 order required all units will construct foxholes minimum 2.5 m deep with overhead cover of logs minimum 30 cm diameter covered with 50 cm of earth. The February 18 revision mandated movement in areas under artillery threat only through covered trenches. All positions must have concrete or steel overhead protection. These Measures were physically impossible under combat conditions. The materials and time required for such construction didn't exist. A February 26 directive simply stated, UNS will disperse to maximum distance combat effectiveness permits. No more than 2 men in any position. The Ludendorff Bridge at Remagen captured on March 7, 1945 illustrated both the power and limitations of proximity fuses. When Lieutenant Karl Timman requested artillery support with VT fuses to slow German retreat across the bridge, the artillery commander refused, citing reports that U.S. troops were too close. This documented refusal found in official U.S. Army history showed that proximity fuses required careful tactical employment to avoid friendly casualties. German attempts to develop their own proximity fuse revealed the true industrial gap between the combatants. Rhein-Needle resumed research in 1944 and actually test-fired several hundred working prototypes before war's end. But prototypes weren't production models. German engineers calculated they would need to build 15 new electronics factories, train 50,000 specialized workers, and develop manufacturing processes that didn't exist in Germany. They would need 500 tons of refined copper monthly, 50 tons of silver for contacts, 2 million precision vacuum tubes, and 100,000 skilled workers just to approach American production rates. Even if materials existed, German industry lacked the precision machine tools required. American factories used Swiss-made microls accurate to 110,000th of an inch. Germany's best machine tools, worn from 5 years of continuous operation, achieved 1000 thin accuracy on good days. But quality control requirements alone exceeded German capabilities. The deeper irony was that German scientists understood the theory perfectly. They had actually begun proximity fuse research before the Americans. But understanding theory and achieving mass production were entirely different challenges. America had not just developed superior technology but created an industrial ecosystem capable of producing it in millions. While proximity fuses transformed ground warfare in Europe, their original purpose, anti-aircraft defense, reached peak effectiveness in the Pacific. By 1945, proximity-fused anti-aircraft shells destroyed Japanese aircraft with unprecedented efficiency. The kamikaze threat, which might have made invasion of Japan catastrophically costly, was largely neutralized by VT fuses. Ships using proximity fuses during the Okinawa campaign shot down 91 Japanese aircraft. For every 100 attacking compared to 25 per 100 before proximity fuses. Admiral Willis Lee stated proximity fuses saved 100,000 American lives in the Pacific. Every Japanese plane shot down by VT fuses was one that didn't crash into our ships. This dual application, devastating against ground forces in Europe, decisive against aircraft in the Pacific, demonstrated American industrial philosophy, mass produce excellence, and deploy it everywhere. Germany, struggling to produce basic ammunition, faced an enemy that put sophisticated electronics in disposable shells. Military researchers studying proximity fuse effectiveness found they were 3 to 10 times more lethal than conventional artillery against ground targets. Against V-1 flying bombs, destruction rates increased from 24% to 79%. In naval anti-aircraft use, the average rounds per kill dropped from over 1,000 to approximately 300. The 50-fold increase in lethal fragment area fundamentally changed artillery employment. Traditional artillery required concentrated barges to achieve area coverage. Proximity fuses allowed dispersed fire to achieve similar effects with fewer shells. This improved logistics, reduced barrel wear, and allowed artillery to support more units simultaneously. General Patton reported that proximity fuses allowed his artillery to support advancing units more effectively. Instead of lengthy preparatory bombardments, artillery could fire shorter, more lethal concentrations that allowed infantry to advance before enemies recovered. This increased operational tempo contributed to the rapid Allied advances. In 1945, however, casualty figures require careful analysis. While various estimates circulated during and after the war, no documented evidence supports Claims of specific large numbers like 250,000 German deaths from proximity fuses. What is documented is their multiplication of artillery effectiveness and their psychological impact on German forces. German recognition of proximity fuse technology came gradually and incompletely. Prisoner interrogations revealed that most German soldiers never understood what was killing them. They spoke of tree bursts and air mines, but didn't grasp the systematic nature of the technology. German technical intelligence eventually recognized the sophistication involved. Captured German reports from March 1945 acknowledged American proximity fuse represents 5 years' advancement in electronics miniaturization. Replication would require complete retooling of electronics industry, new materials currently unavailable, and minimum 18 months development. Recommendation: impossible under current conditions. The German military's final situation report dated May 7, 1945 stated, American artillery employing proximity detonation has inflicted casualties exceeding all other weapons systems combined since December 1944. Countermeasures have proven ineffective. Recommend immediate cessation of hostilities to preserve remaining forces from annihilation by superior technology. The proximity fuse program represented approximately 3% of all American physicists working on a single weapons project. This concentration of scientific talent combined with industrial capacity created production statistics that defied German comprehension. Each production line at Crosley Corporation could assemble 500 units per hour. Workers performed individual operations in seconds with microscopic precision, thousands of times per shift. The facilities operated 24 hours daily, 7 days a week. Christmas Day 1944 saw no production decrease while German soldiers died under proximity fuse bombardments in the Ardennes. American workers maintained maximum output. The supply chain stretched across America. Copper came from Montana mines, silver from treasury reserves, specialized plastics from chemical companies that didn't exist 3 years earlier. The industrial mobilization required was as complex as the technology itself. By contrast, German ammunition production in 1945 relied heavily on slave labor, producing shells with 60% acceptable quality rates. Sabotage by forced workers reduced effective output further. By March 1945, only 30% of German artillery shells functioned properly. American VT fuses achieved 94% reliability despite their sophisticated electronics. The proximity fuse story encompasses more than technology and production statistics. It fundamentally changed the battlefield experience for infantry on both sides. American soldiers gained confidence knowing their artillery could effectively suppress dug-in enemies. German soldiers lost the psychological security that earthen entrenchments had provided for centuries. Veterans' accounts from both sides confirm this transformation. American forward observers described calling in fire missions with new confidence, knowing proximity fuses would affect enemies even in prepared positions. German veterans recalled the helplessness of hearing incoming artillery and knowing that taking cover offered no protection. The medical implications were significant. Proximity fuse casualties presented unique challenges. The downward angle of fragments created wound patterns military surgeons hadn't encountered. German medical services, already strained, couldn't adapt to these new casualty patterns. American medical personnel, by contrast, had penicillin and plasma, advantages that had nothing to do with proximity fuses, but compounded their effectiveness. The proximity fuse represented more than tactical advantage. It demonstrated systemic superiority in connecting science, industry, and military application. While Germany pursued wonder weapons like V-2 rockets that consumed enormous resources for minimal military effect, America mass-produced genuinely revolutionary technology and deployed it widely. The German V-2 program cost approximately $2 billion in equivalent resources and killed approximately 9,000 people. The proximity fuse program cost half as much and transformed both ground and anti-aircraft warfare. This comparison illustrates different approaches to military technology. German emphasis on revolutionary platforms versus American focus on evolutionary improvements manufactured at scale. The proximity fuse also validated American organizational methods. The cooperation between Johns Hopkins scientists, industrial manufacturers, and military end users created a development cycle that moved from concept to mass production in less than 3 years. Germany's fragmented research efforts and inter-service rivalries prevented similar achievement. After Germany's surrender, American technical intelligence teams studied German proximity fuse research. They found sophisticated theoretical work but no path to production. German scientists understood the principles but couldn't overcome manufacturing challenges. The Rheinmetall prototypes discovered in 1945 were technically sound but used conventional vacuum tubes that couldn't survive artillery acceleration. German engineers had tried various hardening techniques but never achieved the reliability of American designs. Even if they had, Germany lacked industrial capacity for mass production. Soviet forces received small proximity fuse supplies through Lend-Lease, but no technical documentation. Soviet engineers spent 7 years reconstructing captured samples before successfully producing homegrown proximity fuses in 1952. Even then, quality remained below American wartime production standards. This pattern of technological transfer revealed the intricacy of proximity fuse manufacturing. Having examples wasn't enough. Successful production required industrial infrastructure, quality control systems, and manufacturing expertise that took years to build. The proximity fuse story offers lasting lessons about military innovation. First, evolutionary improvements to existing systems can be more decisive than dramatic new weapons. Proximity fuses were still artillery shells, but they transformed artillery effectiveness. Second, mass production capability matters as much as technological sophistication. Germany developed jet aircraft, ballistic missiles, and advanced submarines, but couldn't manufacture them in decisive numbers. America produced millions of proximity fuses, each one a sophisticated electronic device, and treated them as expendable ammunition. Third, industrial integration determines military capability. The proximity fuse required coordinated effort from scientists, engineers, manufacturers, and military users. American organizational culture enabled this integration. German institutional rivalries undermined it. Finally, secrecy has operational value, but also costs. Restricting proximity fuse use until December 1944 preserved tactical surprise but caused months of additional Allied casualties that might have been avoided. The balance between protection and operational advantage remains a problem in modern military technology. The proximity fuse raises complex moral questions about technological warfare. It made killing more efficient, more certain, more mathematically precise. German soldiers in foxholes had no defense against shells detonating overhead at precisely calculated heights. This wasn't combat in any traditional sense, it was industrial killing. Yet proximity fuses also shortened the war. Every German division destroyed by proximity-fused artillery was one fewer defending concentration camps. The technology that efficiently killed German soldiers also accelerated liberation of Nazi victims. Admiral Louis Strauss, who ranked proximity fuses among the developments upon which victory very largely depended, understood this moral tension. American veterans wrestled with these implications. They were grateful for technology that saved American lives, but unsettled by its devastating performance. Accounts describe finding German positions where every soldier died simultaneously from airburst fragments, efficient killing that removed human choice from death. The proximity fuse ultimately represented American advantages that went beyond any single weapon. It demonstrated industrial capacity that could mass-produce sophistication, scientific ability that could solve complex problems swiftly, and organizational skill to coordinate development and production. When German infantry faced proximity-fused artillery in December 1944, they confronted more than a new weapon. They faced the physical expression of American industrial democracy, a system that could conceive, develop, manufacture, and field advanced technology while fighting a global war. The 30 feet between shell detonation and ground impact represented the gap between American capability and German expectation. In that narrow distance, measured by radio waves and timed by miniaturized electronics, lay the difference between industrial democracy and totalitarian inefficiency. The proximity fuse transformed more than World War II. It launched the era of smart weapons. Modern precision-guided munitions trace their origin to the miniaturized electronics first used in proximity fuses. The concept of embedding intelligence into ammunition, revolutionary in 1944, is now standard practice. The manufacturing techniques developed for proximity fuses influenced post-war electronics production. The quality control standards, clean room procedures, and precise assembly methods became foundations for the semiconductor industry. The women who assembled proximity fuses in 1944 pioneered techniques still used today. The organizational lessons proved equally enduring. The integration of academic research, industrial production, and military application became the model for Cold War weapons development. The proximity fuse program showed that democratic societies could mobilize technology as effectively as totalitarian states, perhaps more so. This account relies on verified historical sources and documented evidence. Production figures originate from Bureau of Ordnance records. Technical specifications come from declassified Johns Hopkins Applied Physics Laboratory documents. Battle narratives are drawn from official after-action reports and military histories. Unsupported claims have been omitted. No evidence substantiates specific casualty figures sometimes attributed to proximity fuses. German jamming attempts remain unverified. Some frequently repeated stories appear to be composite anecdotes rather than documented events. What remains after careful verification is still remarkable. The proximity fuse was genuinely revolutionary, converting artillery from an area weapon into a precision system. Its development and mass manufacture demonstrated American industrial dominance. Its employment accelerated Allied victory. At 30-foot altitude, democracy defeated fascism not through ideology alone, though America held moral advantage, but through the mundane excellence of mass production. The proximity fuse, miniaturized electronics in an artillery shell, represented everything Nazi Germany misjudged about American democracy. Where Germany saw weakness in diversity, America found strength in mobilization. Jewish scientists who fled Nazi persecution contributed to proximity fuse development. Women who could not serve in combat assembled the weapons that killed German soldiers. Democratic inefficiency somehow produced 22 million complex electronic devices, while totalitarian efficiency couldn't manufacture basic ammunition reliably. The German infantry who faced proximity fuses in December 1944 were arguably among the world's finest soldiers. They had conquered much of Europe, fought on several fronts, survived years of attrition. They died in their foxholes not from lack of bravery, but from encountering the future. They had 30 feet the distance from airburst to impact to realize that everything they believed about American weakness was wrong. In those instants, as fragments traveled from electronic detonation to human flesh, the Third Reich's illusions collided with American reality. The proximity fuse killed more than German soldiers. It killed the mythology of martial superiority, the romance of defensive fortification, the idea that courage could overcome technology. In 30 feet of altitude, measured by miniature radios using technology that shouldn't have existed, produced in numbers that shouldn't have been possible, America announced that future warfare belonged to those who could imagine it, engineer it, and mass-produce it. Every German soldier who died under proximity fuse airbursts died from American industrial philosophy made visible not in ideology, but in engineering, not in propaganda, but in production, not in theory, but in terminal ballistics. The shells that exploded 30 feet above German foxholes delivered democracy's argument against fascism in fragments, proving that free societies could outproduce, out-innovate, and ultimately outfight authoritarian powers. The proximity fuse was ultimately democracy's quintessential weapon, sophisticated yet mass-produced, complex yet dependable, expensive yet expendable. It killed efficiently not through hatred, but through engineering excellence. It ended battles not through cruelty, but through mathematics. It won wars not through brutality, but through industrial capability. The story of German infantry facing proximity fuses is fundamentally about the collision of past and future. Long-standing defensive techniques perfected over centuries became obsolete in minutes. The earth that had shielded soldiers since antiquity could no longer protect them. The proximity fuse didn't just kill German soldiers, it killed an entire understanding of warfare. In December 1944, German infantry had 30 feet before proximity fuse airbursts shredded their foxholes. In that brief space lay the difference between the world that was and the world that would be. They measured their graves in meters. America measured victory in megahertz. The future had arrived. It was mass-produced, and it exploded at exactly 30 feet.